to do this because indexing categories will be usually I, and it's already look like underlined.
So index category is just some category.
Yeah, it's just some category at the moment, no restrictions. So what was the limit? Well, we can think about this D as a kind of diagram in this C. So it means that we have several objects, arrows between those objects, and this cloud is supposed to represent this diagram D. So then over this fixed kind of diagram, which is given by the functor D, well, I prescribes the shape of this diagram. So for example, these 3 objects and 3 arrows, so this is the shape. And then you apply D, you get some very concrete objects, say X, Y, Z, F, G, and H. Now, we define notion of a cone. A cone is an object, say C, or maybe let me call this L. It will be a limit. So L, and we have projections. So to every object in this diagram, so say P1, P2, P3. So this is a cone. The cone meaning that we have object. So L is an object and projections. Pi to the, in general, will be all di's. So we can also write this that this I is in the objects of I. But sometimes for shortness, I'm going just to write I is in the I. And there's a universal property for this cone. You have any other object, now maybe let's call this X, and other projections. So here this will be X1, say here this is X2, and here this is X3. Well, whenever I have projections, the condition that I require is that if I have a triangle with an arrow in this diagram, then this triangle is commutative triangle. So for all possible triangles. So I have this property for the projections Pi. I have these properties for the maps Xi, and the meaning that, well, I don't know, the meaning that this L is universal, that this is a limit, means that in this category of cones, this is a terminal object. So there is a unique map here, say, well, this is supposed to be a map to the L. There is a unique map U, such that all the squares that you can form now are commutative. So there is unique U from the any X to the L, and U, then you apply Pi, you'll get Xi. Again, for any I and I. That's the definition of a limit.
Excuse me, this picture is in C, in the category C, right?
Yeah. So this is kind of part of the C, which is given by the image of this functor. There is object L, which is also in C, and this whole thing has a universal property. So everything lives in the C.
So we somehow want I to be a small category and C to be like some big category.
At the moment, I is any category. I will restrict to the small categories later, but definitely construction makes sense in any for any I.
Yeah.
Right.
Yeah, but what if like C is like I, for example?
We will do this as our first exercise on the seminar. That's an interesting question. Okay, and also we proved the following theorem that tell us, maybe I'm not going to call this theorem, that if we can reduce any limit to two types of limits, so I can form a product over I in the, well, here this is objects of I, take di, I have two canonical maps, so U, I, J, D, J. So with any functor D, you can associate this kind of diagram with just two objects and two arrows. We assume that the products exist. Then if you take equalizer of this thing, then the equalizer is exactly the limit of the functor. Yeah, so in this situation, this object L is the limit of the functor. This is notation. Of course, kind of this a little bit abuse of notation because we're saying that the limit is just an object, but we can see that the limit is actually cone. So the limiting cone, we have object and all these projections. So from this theorem, we can observe immediately one simple but very useful property, that first of all, limit is always a sub-object in the product. No, still the same product. Right? That is because we prove that any equalizer is a monomorphism. And in a concrete category, you can even give a formula for the limit. Well, say limit of a diagram D is, this is the set. Well, now we have elements in the product that satisfy some additional property. Well, we have some sub-object. So I'm going to call this x kind of like a vector xi, where I is in the set of objects. So product d of I is in the I. Well, such that, and the condition is that the image of these two maps are the same, right? When we can compute the equalizer, that's the condition. So here, this just means that d of u applied to the xi is the same as xj, and that's supposed to be true for any arrow u from I to j. Right? That's just an explicit formula for a limit, right? So this is just because we know how we can explicitly compute equalizers. So whenever our formulas for equalizers work, well, like in sets, in monoids, in groups, and rings, we can use this formula for the limit. Okay. Now, next section might have a little bit confusing title, so inverse or projective limits. Well, I mentioned in the beginning that this notion of a limit sometimes also called inverse or a projective limit. So there is another terminology. I'm going to use this another terminology. Well, an inverse, let's say this is definition. An inverse or projective system in some category C is the following thing. So this is a functor D from I to the C, where I is a directed set. Okay, let's continue the definition. So let's say this is one, and second part of the definition, inverse or projective limit is limit of inverse system. So projective and inverse, these are complete synonyms. It's just in the different books you can sometimes meet inverse, sometimes projective. So there is no difference. It's just two terms that could be used as a complete synonyms. And if we have this inverse system, you can define the notion of inverse or projective limit. This is one of the ways to use the notion of an inverse or projective limit to this kind of very specific restricted kind of limits when the shape is predicted by a directed set. But sometimes in other texts, people just use a notion of a limit as a synonym of inverse or projective limit. So the terminology is kind of not the same in all the sources. Well, yeah. So maybe let's understand explicitly what this means. So I is a directed set. Well, it means three things. First, I'm going to assume that I is not empty. Second, well, of course, directed means that I have a binary relation less or equal, and this binary relation is reflexive and transitive. And three, which is most important. So if you have a set satisfying 1 and 2, well, this is called?
Ordered.
No. For a PO set, you need the additional property that this is antisymmetric. And this is called just a pre-ordered set, sometimes preset. Now, directed is a preset that has additional property that whenever we have I and j in the I, there is k such that I is less or equal than k and j is less or equal than k. And of course, any pre-ordered set we can interpret as a category. So clearly in the previous definition, I use this as a category. Meaning that whenever we have this relation, we interpret this as an arrow.
And K is some kind of terminal.
No, not in general. This is just, well, for any objects there is a k with this property. It's not unique. Well, it's not, it definitely does have to be terminal. Well, consider the following example. I think the typical and most interesting in the applications is example in these applications for inverse systems, where we just take natural numbers with the usual less or equal relation. Then for any two natural numbers, you have a natural, well, I and j, you have a natural number which is larger than I and j. Well, clearly this is not unique, clearly this is not terminal. There is no terminal object in this category. Okay. Yeah, and I wanted also to say what it means to have an inverse or projective system explicitly if you have this definition. Well, it's very easy, right? Well, okay, now it's very easy. You have a family of objects, right? So we have objects, and for two objects you have maps. Well, when people want to give a definition of inverse or projective system, they usually don't write this like d of I. They kind of want to pretend that there are no functors and categories, so just writing like this. Object with an index I. And when I have two objects, there is a unique map between these two objects, f, say, I, j. And yeah, and what properties we have? Well, we have first, that the Fii is the identity, and the second property that the composition works. So if I have Fik, then this is composition of the Fj, Fjk. Now clearly, if I have a family of objects and family of maps satisfying these two properties, that's the same thing as a functor from some directed set. Yeah, and in this definition, we continue to assume that they have 1, 2, and 3. Correct this if this is wrong. It's a simple exercise. Probably wrong.
Feels like if Fij is going to divide j,
Yeah, you just need to write ij and k, write the maps, and write the correct formula. Okay. So this is what is the directed system. Именно. Like in natural numbers. Natural numbers is the first example that comes to mind when you talk about directed sets. Okay.
Why do we require this property?
What property?
I think that for any two elements there is an upper bound.
There are plenty of answers to this question. Well,
Because it seems like when we take just the limit,
mhm.
it makes more sense to think about lower bound, not upper bound.
No. Well, in a sense, you're right. Well, this is just a definition of a directed set, and this is what is required in the directed set. But when you want to take a limit, you're definitely right. You want to kind of reverse these inequalities. But you can do this by saying that you consider a situation where you have a functor from D to op C.
Oh yeah, I see.
So that is not a problem. And sometimes this is called upward directed because of this property, and the opposite will be downward directed. And why directed limits are interesting? Well, first of all, there are examples which are interesting in applications of directed limits, especially just with this directed set. And then there is a general one theorem that also shows that this is an interesting class of limits because it's related with the general limits. But we will do this in several minutes. Okay, I want to start with examples. Wait, sorry, there need to be a correction here. Thank you for this comment. So that's a definition, standard definition of a directed set. Now, because I want limits, I want opposite in the definition here. So I need to correct this definition. So with that definition of a upward directed set, I need op here.
So that's a directed limit then?
Yeah, that's a directed limit. So you need to take a directed set in the sense of that definition and then take the opposite.
Is it the same if we just say that phi is a set that satisfies the property that there is a lower bound?
Yeah, I just said that, yes. The reason why I'm using this definition, because usually in the literature you can find this definition, and then you use opposite here. Okay. Okay, now everything is fine with the formal definition, and an example is the completion. Opposite category.
Yes, if we write I-op, it will be reversed.
Exactly. With this definition of a direct set, this is the correct definition of an inverse system with the opposite. If I remove the opposite, this will be a definition of the inductive or the direct system, which we're going to use later when we discuss colimits. Okay, completion. So let R be a commutative ring. Take an ideal and a module. And I can do the following. I can start with the quotient of the m modulo im. Then there is a projection from the m modulo I squared m. Do you have questions about what we have in this diagram? Because if you don't understand something, you won't understand the rest. The question is it clear what I wrote here?
Yes.
Does this structure give to a module some additional properties like?
No, you
in
can.
particular, I squared m and im. Do they give some additional properties to a module? Like
No.
it's
It
some
could be
kind of normal subgroup of m, and then it's some kind of lower central series. No, it's not.
No, no. You can take any ideal and consider submodule. Here, elements in this submodule just finite sums element in the ideal times.
A normal subgroup as a module is a normal group as it's abelian.
Yeah, everything is abelian from the point of view of groups, so there is no problem. Well, the observation is here that you have this I squared m, and this is a submodule in the IM, right? Because I squared is in this subideal in the I. Hence, there is a projection, but we just this is just a quotient by IM, which is considered as a submodule inside M modulo I squared m. Okay, and then we just continue doing this. right? You can see that in this case, the directed set that I use is just n, right? So in the n, I have 1, 2, 3, etc. And since I take I op in the definition, I inverse all the arrows. So I get the diagram like this. So for any module and any ideal, we can form this. And now you can form the limit. And this is where it's convenient to use notation when n belongs to the I, right? So this limit, this is by definition completion of a module with respect to the ideal. So sometimes it's also called I-adic completion.
Sorry, what is the category C here?
Category C is the category of all R modules. Yeah, let me write this. So just give me a second to write this. So what's the question?
N's in the limit and in the degree of an ideal are different ones.
No, it's the same n. So this is n equal to 1, 2, and 3, and this is general formula. Right? To form an inverse system, I suppose to take a bunch of objects, in this case parameterized by natural numbers, and the maps. And you can see that the maps are in the right order, right direction, because of this I op.
And can you repeat, you had some discussion on that border blackboard about some opposite arrows, and
Yeah.
I completely missed it.
Well, that's the definition of a directed set.
Yeah.
With this definition, n is a directed set,
Yes.
which is nice. Now, here n is this kind of shape of the diagram. Now you can see that in my example, I have arrows in the other direction. So it means that if I want to consider such examples, I need to put opposite in the general definition. Otherwise, it just don't work.
Oh, okay.
Sorry, and the last line in the middle blackboard, is it like definition or
Yes.
statement?
No, that's a definition. The completion of a module with respect to an ideal is the limit of this diagram.
Yeah, so here we have like very special case where I is actually a subcategory in I.
It's a case where the index in category is just n opposite. Well,
Oh yeah.
if you use this definition, then I is just n. Opposite is here. Okay, so example of this example is the following: the ZP. So these are p-adic numbers, and you can just define this as a limit of the z modulo p to the nz. Again, you can write n belongs to the n, but you can also skip this. So that's one of the possible definitions of p-adic numbers. There are other definitions that use some topology, some series, etc. Yeah, and one more remark. Remember that before I was also saying that for the limit, there is notation with the arrow that goes like this. Now you can see the reason why this notation makes sense. Because this is kind of, in this limit you go in that direction. So inverse of projective limit, in the notation, sometimes people use arrow that goes in this direction. Well, because you can do also the opposite thing. You can consider limits in the other direction, where you don't put opposite here. But this would be an example of a co-limit. So this would be.
Okay, and this is an example of co-limit.
No, that's a limit.
That's the limit.
They're all
Yeah, they all are limits.
Then I don't see why you're using the arrow of that direction.
Well, because look at this diagram.
Okay.
What you're supposed to see here is something like a module which is becoming larger, and larger when you go in this direction.
Yeah, but it's going that direction.
The arrows are going that direction, but the limit is kind of going in the other direction.
Okay.
So that's the reason for this notation.
So all
No, everything can limit. So meaning that if I want to understand, for example, if I want to understand what this is explicitly in terms of elements, well, it means that I have, so that's the definition, it means that I have these periodic numbers, I have projections n plus 1. And for any n, this is commutative and also has universal property. Okay, do you see how to describe elements of these periodic numbers explicitly as elements?
Well, yeah, it's just an object of product. So it's just all sequences.
Yeah, for example, when you take n equal to b1, this is just element in the z modulo p, right?
Yeah.
Then the next element, so I don't know, maybe I need to write, maybe I don't, okay. This will be just a a0, an element here. Now, here you'll get some element, maybe let's call this a1, right? And what are relations between a1 and a0? Yeah. So how we can write this a1 in a more convenient way? So let's say we have, again, some a0 plus now a1p, and this is the class modulo p squared. This is the class modulo p. Now we can see that the condition is exactly that this a0 is the same as this a0, because we consider this modulo p now. Right? So consider modulo p, this goes to the kind to 0, so a0 here is the same as a0, so a0 is the same as a0 with the tilde. And then you just continue doing this. So if you have an element here, you just add, so here it will be sum ai p to the I is running between 0 to the n minus 1, and here the sum will be ai p to the I is between 0 and n. And this maps is just takes this element and computes this modulo pn, so exactly like in this example. So at the end, when you consider, well, this is a product, so you can take the sums of infinite lengths, then periodic numbers, this is just ai p to the I, or such sums, such that, well, we can assume that ai, oh, we can say that these are integers between 0 and p minus 1. Well, the universal property I'm going to leave as an exercise.
Is it somehow non-trivial, or it's just too hard to check? Like,
No, I don't think that there's anything hard about this. Well, the answer we get by the theorem that we proved at the end of the last lecture, right? So this follows immediately. And because that theorem give us a limit, we automatically get universal property. That's one way to show this. And another way is just do this directly.
yeah, but there we will need to find some equalizer or some structure, right?
Mm,
It's not direct, it's not really obvious what to do, to be honest. I mean,
No, everything is completely obvious, because in the beginning of today's lecture, I rewrote this formula for concrete categories. And then I just apply that formula to this case.
you mean the one with equalizer or something else?
I wrote a formula that the limit is elements in the products that satisfy additional property.
Yeah.
And if you just look carefully at that formula and this formula, you can see that this is just an example of the general formula. No, that formula is essentially saying that you have all the you'll have element here, element in all this z modulo p to the n, such that when you say take this element, compute this modulo p, you'll get this element, meaning exactly that this constant is the same as this constant. And then you do this for any n, and you get exactly that on each step, if you already have this polynomial in the p, and on the next step you just add one more power of p and one more constant. And then at the end you get this formal series. Okay, and another example, which probably might be a little bit easier to understand, take a limit, so inverse limit, in the case you take polynomials and variables and modulo ideal generated by all these variables. So what's the limit in this case? Yep. And the reason for this is more or less the same as in the previous example. Well, anyway, so I'm going to leave this as an exercise. Maybe if you have time, we do this on the seminar. Okay, these are examples. So the completions, well, there is one more example, the total completion. Well, total completion of z, let's say. We can do this in general, but for z it's already interesting. So here I, as before, is the set of natural numbers, but the pre-order relation is a little bit different. So let me write this. I'm trying to draw this differently. So if n is less or equal than m, well, this means by definition that n divides m. You can check that this is again a directed set with this relation. Now we have, of course, maps f and m from the z modulo mz to the z modulo nz. Again, just projection, right? Since nz is an ideal, corresponds to an ideal in the z and contains mz. And total completion of the integers is just the limit in this case.
It's a directed, so the arrow would be.
Yeah, but well, if from the point of view of general limits, this is just the limit, and if you want to keep this arrow, well, you can draw the arrow. It's still a limit, so arrow goes in the same direction. Okay, so this is called the total completion of z, and sometimes this is called profinite integers, I guess. And the completion in general, for example, if you go back to the p-adic numbers, this is an example of a profinite group. In general, definition of a profinite group, this is a limit, well, inverse limit or projective limit in the category of groups, but all these objects that you have, d of I, are finite groups. And in this case, you can clearly see that all the groups are finite. So that's an example for profinite group. And the completion of z is also an example for profinite group because all these quotients are finite groups. Well, profinite groups, you can naturally find many applications. For example, in the Galois theory. If you do Galois theory for infinite algebraic extensions, the Galois group is a profinite group. Well,
If we're doing algebraic extensions, on these extensions, if you apply automorphism of that group,
yeah, the Galois group.
Galois group, it's a profinite group.
Yes. I can give you several exercises if you're interested in these profinite integers. You can prove that this is a product over all primes of the p-adic integers. And also, you can prove that this is the same thing as the endomorphisms over Z of the Q modulo Z. Couple of exercises, but it's not really category theory, so that's something that we don't going to discuss on the seminar. Just interesting facts to know.
This is endomorphisms as Z models, right?
Yeah, as abelian groups, yes.
Do these endomorphisms have some ring structure?
Well, any endomorphisms have a ring structure. You can compose endomorphisms.
Yes, of course.
Okay, finally, a proposition that I promised already. So if C has finite limits and inverse limits, then C has all small limits. Not only this gives us some examples, interesting in applications, from theoretical point of view, it's also interesting. It's enough to require finite limits and inverse limits to get all limits. Well, this means that the category is finite. I is finite, meaning that finitely many objects, finitely many arrows. So, before the proof, a category I is finite if, well, the set of objects of I is finite and the set of arrows in I is also finite, and you consider a diagram with I finite, then the limit is called finite. We already know some examples of finite limits, products, equalizers. This is an assumption that I is a small category. Objects form a set, yes. No, there is no question to ask, is it true that arrows form a set in a small category?
Yes,
Why?
because between each two objects there is only a set worth of arrows,
Mm-hmm.
and there is that set worth
Yeah.
of objects.
So union of a set over a set is a set.
And does this proposition mean for some I or for every I? Like for every finite?
No, this means that you have all finite limits.
Oh.
This has finite limits, all of them. And all inverse limits.
And inverse limits also finite or not necessarily?
No, we just saw an example of completion with infinite string of objects. So inverse limits are not necessarily finite, no. Well, that is the point, because if that was a finite, well, we still get something finite. We won't be able to do infinite. Okay, but what we really need to prove this? Well, if you have finite limits, we already have equalizers. If you have equalizers and all products over sets, then we have everything. So it would be, to prove this proposition, we only need to prove that there are products indexed by sets. Proof. So if I want to compute a product indexed by some set I, this is the inverse limit of the finite subproducts. So essentially this one formula is a complete proof of this statement. Now I can do this a little bit with more details, right? If I have the following, say I take two finite sets, so J sits inside K, and of course everything is inside I. Maybe they coincide. J is finite, K is also finite, right? And then we have projections. So this is a product over I in K, and this is I in J. And for this infinite product, so I is in set I, we also have projections. So this is Pj, and this is Pk, right? Do you see why we have all those projections? Well, canonically, it is given to us that we have all projections where this I and J are just singletons, right? But now I have a projection, say, to this finite product. Why there is a projection like this?
Well, because by definition we're given projections and
Yeah.
we're index by an element of K plus
In J in this case, yes.
in particular index by an element of J, yes.
Yeah.
J is a subset of K.
So because we all have individual, well, we have all individual projections. Well, hence we have, for example, for this product, we have individual projections to each of these factors. Hence, by universal property, there is a projection like this. And the same will be true here, and the same will be true also here. Yeah, because there are projections to individual factors, and then we use this condition. So indeed, this product over set is a cone over these products over finite sets. Okay. Now the question is how we can show that this is a universal, meaning that this is a terminal object. So suppose I have some other test object f. I have some projections. So this is fk, and this is fj. So why there is a unique map u here? Yeah, the logic is more or less the same. If you have all these projections to all these finite products, in particular you have these projections for singletons, and then by the universal property of this product you get the arrow. And this makes this formula correct. No, this makes this formula kind of proven. Right? So we prove the formula by this argument. Okay.
Sorry, why do you need exactly like this formula to prove the statement?
Well, if you have finite limits, we have equalizers already. Equalizers is finite limit, so we have equalizers for two arrows.
Yeah.
And we know that we have all small limits by that theorem that we proved at the end of the last lecture. We have equalizers and all products, because everything can be reduced to the equalizers and products. So the only problem is to show that we have products parameterized by sets.
So we might have a situation where we don't have products by sets.
Sure, why not? Like in the metric spaces. There are no general products parameterized by sets.
We'll end up in some other category, right? Not in which we want.
Well, you could have different explanations, but for example, you can just say that there are no products in the category. Take, for example, category of finite sets. They take infinite product. It's in general it's infinite set, so it's not in the category.
Showing that it lies inside the category.
Well, yeah, I don't really like this lying inside the category, because in the examples, yes, we know what we're doing, but so if you look at this as an abstract property, you don't have this, like there is an over category for C, in such category we have product, and the question is, do we have this product in the subcategory C? Well, for the point of view of C, we can just say, does it exist or it doesn't? That's all.
But this kind of is like we want it to be like this. We want it to be the limit of this thing, right? Or
Well, I don't know what we want. We just see that this formula is correct, and this formula presents a
if you're
product.
Saying, if you're saying that we don't have that on the left, right? How we can say that it equals something on the right? Like I don't understand this.
No, the formula is saying the following. If we know that we have finite products, and we know this because of this assumption, and we have inverse limits, we know this. We take the inverse limit of these finite products, we'll get something. Well, it definitely will be something in the category,
Yeah.
and there's something in the category is in fact isomorphic to this product.
Oh,
So this product also exists.
okay, I guess I understand.
Okay. Complete categories. Well, now I'm just going to repeat the definitions that I already have in the kind of as a remark for the previous proposition. So first, a category is finitely complete if it has all finite limits. Again, finite limits means that the index in category I is finite as a category, finitely many objects, finitely many arrows. And 2, a category is complete if it has all small limits. Now meaning that the index in category is small as a category. So objects form a set.
What is small limit?
Limits for the category I, and I is a small category.
Oh, I see.
Theorem, I guess. The following are equivalent. So 1C is finitely complete. 2C has finite products and binary equalizers, meaning that we have equalizers for 2 arrows. And we already know this. This follows from the theorem at the end of the last lecture. 3, we can reformulate this a little bit differently. C has finite products and pullbacks. So equivalence of 2 and 3, this is the only thing that we don't know in this theorem. There is also 4. So C has a terminal object and pullbacks. But clearly 4 is equivalent to 3. So just a statement. So the only the trivial part is equivalence between 2 and 3. And this we do on the seminar. It's not really hard. So proof is exercise. And the same theorem, now version for the small limits. So the following are equivalent. 1C is complete. Again, by the same theorem at the end of the last lecture, C has small products meaning that this is products over sets and binary equalizers. 3, C has the same thing, small products and pullbacks. 4, the same restatement. C has terminal object and small pullbacks.
What is a small pullback?
Well, this is a pullback for a family of maps. And this family of maps is a set. So to be completely precise, in the 3, I need to say these are binary pullbacks for 2 maps. And finally, 5, that we just proved, C is finitely complete. And has inverse limits. Again, clearly, by what we already know, 5 is equivalent to 1. So the same question here is how to show that we have, when we have products, that the binary equalizers is the same thing as binary pullbacks, that these two things are related. And we saw the same problem in the previous stream. So that's only one problem for the seminar. Yeah, so the equivalence of 3 and 4 is clearer. Well, if you have a terminal object and small pullbacks, you take pullbacks over the terminal object and you get small products. And of course, if you have small pullbacks, you have binary pullbacks. Okay, now let's switch to the next section, co-limits. The theory is kind of dual, so I'm not going to repeat any theoretical statements. So there's an exercise for this section. Formulate and prove all the dual statements. Like, for example, you can formulate all these theorems for introduce notion of co-completeness and prove the corresponding theorems. But examples are different and maybe even more interesting. So a co-limit of a functor, again, I'm going to call this functor D for the diagram, so is the following. So co-limit I D, this is by definition limit of the opposite category of the opposite functor, and then I need to take the opposite of the answer. So this is obtained by just complete dualization. So if, well, since you start with the limit, you get the following. For the limit, lim I op d op, it has projections. So there are projections pi to the d op I, right? Now, this is in the category C opposite. Or maybe I need to make a remark that d op is a functor from the I op to the C op. And as a functor, it's actually the same functor. Just double dualization give you the same thing.
Shouldn't be from I to C op then? Because
What's the functor from the I to C op?
oh yeah, I see.
Because you have dualization here and here, it's actually just the same functor from I to the C. Now, let's look at this thing. This is a limiting cone for this limit. And if I apply op, well, what it means that this is a cone even? Well, it means that I have limit over I op, d op. I have projections, say pi to the d opposite of I, another projection pj to the d opposite of j, and here I have the opposite of some u, and u is a map from I to j. Well, if I take this is in the category C op, right? Now, if I go to the category C, I'll get the following. So I apply the op to the limit. This gives me the co-limit I d. And then maps go in the other direction, and I'm going to call this maps qi and qj. So qi is just pi op. Now here I'll get di, du, dj. So if we just use all these opposites that you have in the definition, you end up in the following construction. So as before, we have category C. In this category C, we have some cloud that represents this diagram given by functor d. So some objects, arrows. Now, in the co-limit construction, you have kind of maps go in the other direction. So these are called co-projections or injections. So co-limit is another object, and here we have maps, say Q1, Q2, Q3. And if you have any other such map, say some X, this is X1, X2, X3, the universal property give you a unique map U from the co-limit to the X. So you can take this as a definition, as I did, and then do this little exercise to check that everything's actually correct. That you end up, if you just rewrite this definition explicitly, you end up with such diagram as there, and the universal property, because we now work in the opposite category instead of the terminal object, we get an initial object in the cone category. And this data, when you have an object, maps to the object from the diagram, such that whenever you have a triangle, this triangle is commutative. This is sometimes called the co-cone. So co-limit is an initial object in the category of co-cones. Of course, you can repeat the definition as we've done with the limits with the natural transformation, with the comma category and natural transformation. So still the same thing. But sometimes it's, I just gave this formula in the definition because sometimes you want to prove a dual property, and from this definition, when you take the d op and then another op, you can kind of derive some theorem for the co-limits for free. Just plug in one formula into another and get the answer right away. Here, with this such definition, you kind of need to repeat the definition, but repeat the constructions, but in a dual way. So reverse all the arrows and do this by hands. So, okay. Dun, dun, dun. Remarks. Well, first of all, there is another notation and terminology. So co-limits are also have notation lim, and they go in this direction, and also called direct or inductive limits. So this is where terminology becomes completely awful. Co-limits are direct or inductive limits. Unfortunately, this is how historically we have terminology in this area. Well, I guess that is because in the beginning people just realized that they're interested in the direct limits in some categories, and then they noticed that from the general point of view of the theory, these are co-limits. So there is an attempt to fix this. Sometimes people talk about direct co-limits, but it's not used by everybody in the area. So this is 1, 2. As before, and as follows from the definition, co-limit is actually a functor from the category of functors to the category C. And now we have for the delta functor, we have limit, which is the right adjoint, and the co-limit is the left adjoint. So for the right adjoint, we already know this, and for the left adjoint, well, we can prove this formally if we just use my definition, and you can see the following, that the maps in the category C from the co-limit to some object x are naturally equivalent to the maps in the category of functors I, C, D, delta x. So you can check this formally, or you can use this definition and see that this natural bijection is induced by compositions with the coprojections. Okay. Now let's look at some examples. So coproducts. Of course, now when we start with the general definition, we can define coproducts as co-limits of I, D, and in this case, I is a set. For example, set with two objects. That would be a binary coproduct. So if this is a set, then if I say that d of I is equal, say, to the xi, the notation is this, as for disjoint union. And we have coprojections qi from all objects. I is an I. And for example, if you consider the situation of the binary coproducts, well, there is a notation. So we take coproduct of two objects, and then you have two coprojections, say, okay, Q1, Q2. Right, then if you have some object Z, and you have kind of maps to this object, so say this is Z1, this is Z2, then there is a unique map here. I'm just repeating general definition for this particular example. There is notation for this map, and this is the only reason why I want to draw this diagram. So the notation is Z1, Z2 in brackets. And then for the dual construction with the products, we gave some definition of the diagonal map and proved some properties. But we can do the same here. There's a codiagonal map and it has corresponding properties. So I'll leave this as an exercise. So let's take examples of the coproducts. So examples of examples. So first, sets. What is coproduct of two sets? This is disjoint union. And this works for binary coproducts and for any number of coproducts. Let's go to the R modules. This is kind of interesting example. What's a coproduct in the R modules? Hmm? Well, if you already know the answer, yes, this is direct sum. But notice that this is different from the product. You know the difference? Here we have all the vectors, right, with all possible components, and here vectors have only finitely many non-zero components.
But it's the same if I is finite.
Yep, it's exactly the same if and only if I is finite. In general, they are different. For this thing, we have projections with the universal property, and for this thing, we have canonical injections with the universal property. If you try to switch them around, you won't be able to prove the universal properties.
This is applicable to all universal objects, not only R modules.
What do you mean?
Well, not only abelian groups, but some universal.
Well, if you want to say that, for example, if you want to a general relation between limits and colimits for R modules, well, you can say that limits are sub-objects here within obvious conditions, and colimits will be quotients by the duality of such things by some submodule. So if you can do this for not just products and coproducts, but for limits and colimits. Okay, 3 groups. So what if I have two groups, say G and N? What is coproduct in the category of groups?
What is N?
N is another group. G and N are groups. Yeah, free product of. So this is a free product. Maybe let me remind you what a free product is. If you write a presentation for the G, say you have generators S G and relations R G, and the same for N. N has generators and relations. You know this notation, right? This is just the presentation of group in terms of generators and relations. Then you can define a free product of two things in the following way. As generators, you just take generators for the two groups, and you just use the same relations that you already have. Our typical example would be something like this. Fn is a free product of Fn minus 1 with Z, right? It's inductive definition of a free group on N generators. N is a finite number, finite ordinal.
I mean that there are just no relations there and there, so it just adds one more generator.
Yeah. So that would be a special case where this is empty and this is empty. And well, S is a finite set and S is just a singleton of the second group. Okay, 4. Rings. So what is coproduct of the rings R and S?
Some kind of cup product.
I don't know what's cup product. I only know cup product in topology.
Well, I mean, like ICP
Well, it's also something like a free product.
Yeah, this is called free product of rings. By the way, I leave this as a little exercises, and I hope that you can do this, that with this definition, you can check the universal property. And even for sets, this makes sense to check. And even for R modules, if you haven't done this before, you can check this. Yeah, what's a free product of two rings? Well, you do the following. You take the tensor algebra and take a quotient by ideal I. So the tensor algebra T is a tensor algebra over integers for the module, for the abelian group R plus S. And the ideal is the two-sided ideal generated by the following relations. So R product with R prime minus R prime, S tensor product with S prime minus S prime, 1R is the same as 1S. That's the definition of a free product of rings in terms of generators and relations. Of course, you can say that by definition, free product of rings is just a co-product of the category. That's a reasonable definition without any generators and relations. But what we do in the examples, we try to relate the universal constructions to some constructions with elements. And if you do this for rings, that's what you're getting. Okay.
Does this ideal have some special name?
No, I don't think so. At least I don't know any name for this ideal. Okay, commutative rings. Let's take two commutative rings, and what's the coproduct of commutative rings?
Is there any tensor product?
Yep, in this case that's easier. Again, if you know the definition of a tensor product, check the universal property. Okay, let's go to the co-equalizers. Okay, recall that we have the following situation. We have two objects. Let's start with the binary co-equalizers. So we have two objects, two maps. So we want to find the map Q to the object Q such that whenever, well, of course, the condition is that if you precompose this Q with F, you get the same as a precomposition with G. Now, if you have any other object and a map with this property, maybe this is H, right? So FH is equal to the HF is equal to the HG. Then there is a unique map U. So that's the definition of a colimit for a diagram I that just looks like two objects, two arrows. Okay, so let's do this in sets. So first in sets. And even in sets, this is interesting. So what's a notation for the pair Q and little q is co-equalizer of the maps F and G. So now we have sets. Suppose X and Y are sets, F and G are some maps. What's the co-equalizer of this thing? That's correct.
Maybe include f of x and g of x.
But how you can do this?
Well, you find the smallest equivalence relation containing all relations of the form f of x equivalent to j of x.
Yeah, so
And then take a quotient.
we have T, which is just all the pairs f of x, g of x. So this pair is a subset in Y cross Y, and of course X is in ZX. So that's a binary relation by the definition. It's not necessarily an equivalence relation. So let's say that R is TE. So the equivalence relation closure. Well, maybe I just draw this again. X, F, G, Y. Here for Q, I take Y modulo R, Q. And then now it's easy exercise to check that the universal property is satisfied. But maybe I just want to say a little bit more about the equivalence relation closure. So we can define this in a completely formal way. That's the binary relation. In the binary relations, you have equivalence relations, well, relations that satisfy these three properties. You can kind of take the smallest equivalence relation that contains the given binary relation, or you can take the same thing is to say that you take intersection of all the equivalence relations containing T. Well, clearly this is not empty, for example. This is an equivalence relation and it contains T. But you can also do this in a more concrete way. So let's introduce notation. So let's say that we have, say, A to B if AB is in the binary relation T. Then we can say that maybe C is equivalent to D if you have a zigzag. So C is mapped to x1, then there is mapped to x2, etc. And then there is a D. So we just introduce equivalence relation like this. C is equivalent to D if there is a zigzag with some objects X in the middle. And each of these arrows is just this by definition. You can check that this is an equivalence relation. This is indeed the minimal equivalence relation containing this given binary relation. And with this definition, it is much easier, I think, to check that this thing has a universal property. Okay. If you do this, for example, in algebraic categories like monoids or groups, well, you can do the same thing. You, by definition, get some binary relation and you take the congruence closure. So in this case, R will be the congruence closure. Meaning it's not just equivalence relation, it also has to satisfy binary operation. You can do this in topological spaces with the quotient topology. So for topological spaces, everything is nice. Well, for example, if you take R modules, then this is much easier. So in this case, if you want to take equalizer of the two maps, well, you just take a quotient of the n by the image of the f minus g. That's a co-equalizer, and we see that, for example, in the abelian groups, R modules vector spaces co-equalizers are the same thing as co-images, co-kernels. That's right, yes. I think you need to do something like this. You have f and g, you take a set like this, and then you take the smallest normal subgroup containing this set. Yeah, this is how this works in the groups. Okay, and finally, push-outs. So this is a colimit where the diagram is 3 points and 2 arrows between them. Usually people write push-outs in the following way. There is Z, there is a map to the Y, so let's call this Q. Or maybe, I don't know, maybe let's call this G. Let's call this F, map to the X. And then there is object, which is X, like coproduct with Y, but over Z. And this is an initial object in the category of the co-cones over this diagram. So whenever we have any other object, say Z, here you have Z1, here you have Z2, such that the square is commutative. There is a unique map U here. Okay. How this works in the sets.
Well, I think the only thing we can do here is we take a disjoint union of X and Y and quotient by again the smallest equivalence relation generated by the relations of the form f of z is equivalent to g of z.
Yeah, that's right. So if you want this, you just take this joint union modulo some equivalence relation R. And this equivalence relation R, well, again, you'll get T, which is the set f of x, g of x, all these pairs, such that x is in x, and R is an equivalence closure of the T.
Прошу прощения, а вот в диаграмме справа это один и тот же Z? Слева сверху и справа снизу это один и тот же Z в правой диаграмме?
No, thank you. Say this is F. Okay, so what are what is a push out in the category of groups? Yeah, so our notation is this, and this is called amalgamated product of G and N over K. Yep, the statements of the one-compens theorem is the statement that P1 preserves coproducts, well, with some additional assumptions, of course. Okay, and you can see that you can repeat these constructions. If you want to compute limits, we saw that you need to take products and then sub-objects in the products. For the co-limits, you need to compute coproducts and then put some equivalence relations on the coproducts, or take quotients of the coproducts by something. You can do this for rings, for example. That would be just a tensor product, just a free product of two rings over of another ring, again, you start with the free product of rings, then take a quotient by some ideal, generate by the differences. So you take differences of one thing minus the second map, and then take the smallest two-sided ideal, generate by this set. So I don't think that we really need to write all these formulas. Maybe, I think I'm out of time, so let's take a break.
Can you give an example? Is it possible to make an example of the push out on category of topological spaces, for example?
Sure.
Because I'm sure I've heard of it, but
Yeah, so for
now.
topological spaces, this is like something like a gluing construction. So I think a nice example would be something like this. You take S1, you embed S1 into D2 just as a boundary, and do this again. Now, if you want to compute such push out, you kind of have one copy of D2, another copy. So this is D2, this is D2, and this is S1, which is in common for this D2. So this is S1 embedded in the D2, and again. So what you need to take a push out? Well, first of all, you take a disjoint union, and then you need to identify in this disjoint union you get some equivalence relation. So equivalence relation here would be that any point on the boundary is identified with the corresponding point on the boundary of the second copy of D2. So kind of glue these two disks together, and what you get is S2. So this gluing construction in topology, these are all examples of the push-outs. For example, also, this is what you do when you discuss manifolds. You take covering by open maps. Again, covering by open maps. Inside this covering, there are intersections. Right, so there is a map U alpha, not map, chart. There's a chart U alpha, another chart U beta. Here in the intersection is U alpha beta. And here this is coproduct of all alphas and betas. So alpha, say this is beta. So then what's push out of this diagram?
Atlas.
Oh, this just to be the manifold with this atlas.
Okay.
This is exactly how you glue a manifold from the local charts, yes. And of course, you can construct plenty of such examples. You can in the topology.
Can you glue something like a sheaf out of these things?
I think gluing of sheaves is a little bit different. The push-outs probably won't be enough. Yeah, for glue.
If you take a forward of sheet along and immersion, and then you glue these things along the bushboards of intersection, I think you will get exactly.
I think the question was how you can describe all the sheaves on the manifold.
Well, I think it is the same thing. No? So,
It is.
What is a function on the manifold? It is a collection of functions on how to say sheets?
Charts.
Is
On-
locally arranged
Charts,
space.
which agree on intersections.
Yeah.
So
Yeah, but this is how you glue sections of a given sheaf. I think the question was you have a sheaf on each of these charts, and you want to glue a sheaf on the M. So
but what is the difference?
the difference is the gluing data. You need some additional isomorphism. So for example, you need to have something like you have a sheaf on U alpha, you have a sheaf on U beta, you restrict them on the intersection. There is an isomorphism between one restriction and another restriction. So you see this is different data because they don't just coincide as elements in the set. There is an isomorphism between two sheaves living on the U alpha, U beta. And this will be, I think with this data you can do this. but it's not just a push out. I think it's a little bit more information than that. Oh, anyway, so let's take a break.
Well, yeah, we must have something like a cosine conditions, right? And
Yeah, for this isomorphism, we have cocycle conditions.
this is not accounted for in the push-out construction in any way.
Just additional data. ядро это коуравнитель функции и нулевой функции, а это будет что-то другое. Well, actually, now I remember one more interesting example of push-out I just want to tell you. Maybe it will be useful for you to doing something. And it's also related to one of the problems in the first quiz. So let's take the following situation. So H and G are groups, and suppose you have a group map. Yep. So let's return to this situation in a second. But to think about the situation, I need the following push out. So let's X be an object in the category of the right G sets, and Y is an object in the category of the left G sets. Okay, so then I take the following product of X, G, and Y. Since there is an action, say G acts on the X on the right, so here we have a map action on the X, product with the identity on Y, so this will be X and Y. And there is a map identity on X, product with the action on Y, so this will be X product with Y, right? For any two G sets, one is left, one is right, and for any group G, we have this diagram.
And what kind of structure will it inherit?
Well, the question is, what's push out of this thing? And push out has a special name, this kind of product of two G sets over a group. It will be, but I need to start with this general definition. So this is how I define this product of two G sets over a group. You can see this is looks a lot like a tensor product of two modules. Right, because for example, an analog would be you take an algebra over K, you take two modules, and then you have, say this will be right module, algebra, and the left module, then the action map would give me M, and this is tensor product over K. This will be tensor product over K. This is also tensor product over K. Well, what would be the push out of this diagram in the category of modules? Yep. This is more or less definition of a tensor product, because here we have, this is linear in the first, linear in this, well, it's not linear, additive in the first, additive in the second, but here when you form this push out, you additionally add the relation that you have MA tensor N is equivalent to the M tensor AN. So push out is adding to you this equivalence relation. And the same works for the groups, right? So in this push out, well, this X a product over G with Y, notice that the notation is quite unfortunate, because this is a supposed to be something like a coproduct, and we use notation with the product. But anyway, this is standard notation, at least in topology. So here I'll take X product with Y, and equivalence relation. And equivalence relation more or less the same as for the tensor product. I have X G Y is equivalent to the X, and I move G to the second factor.
And it would be, so you want this product in the category of just sets, right?
Yeah, so this is in the sets. It is possible to do this in other categories, where you can take any category, define group in this category, and try to do this construction, but let's do this in the sets. Or for example, what will I get if I take a singleton, take a product over G with some Y? And just look at this.
Well, because on the point G has triggered it.
Yep. This is the set of orbits. It's just, if you just look at this equivalence relation, and in X you have only one point, then, well, this would be exactly all equivalence classes. And of course, the same formula would work if you, instead of Y, plug in a point. Okay. Now let's return to this situation. We have two groups and we have a homomorphism between two groups. Now, of course, there is a functor, let's call this F upper star, from the G sets to the H sets, right? Now we have a G set, automatically H is acting on G using this homomorphism F. Now I claim that this functor has left and right adjoint. So what's a left adjoint? So on the left adjoint, so this is another direction, so I'll start with an H set. So X is an H set, so I want to construct a G set. Well, as for the modules, you can do the following. You take a product with a G over H and X. So this is kind of induction, but in the category of the G sets. And there is a version of the co-induction. Again, X is an H set. So now we have a home over H, G, X. Sorry. Thank you. So if you look at these formulas, it's not very hard to actually show that this is indeed the left adjoint and the right adjoint for any group homomorphism. And the formulas are exactly the same as induction and co-induction for the map of two rings.
What is H
Hmm?
What is H
H is a group.
No, here.
Here?
It's homes.
Ah. Yeah, so these are homes in the category of, well, I can as well write H sets, but when I do some explicit computation, some categories like modules and G sets, I prefer home. So this is H sets between G and X. Well, X is a given by definition the structure of H set, and if this is a group by this homomorphism, H is also acting on the G. Okay. If you take H to be the trivial group, which is also possible, and this will be just the embedding of a trivial group, you'll get the problem from the last quiz. But you can see this works in general, and the picture is completely similar to the picture for the rings. Okay, so first problem for the seminar, I stated this theorem about well, the fact that if we have products in the category, then we have equalizers if and only if we have pullbacks. So let's prove this.
Could you repeat the problem?
Yeah, I'm just raising the whiteboard and then I formulate the problem. So first, so C C has products. So show C has binary equalizers if and only if C has binary pullbacks. If we can show this, then we actually proved two theorems in the section about complete categories, because this is the only thing that was missing. Okay, let's other people think about this. So if you already saw this, maybe I can ask you one interesting question. Do you want an interesting question? So it's quite a general situation as we have from the lectures. You have functor from some category I, the category C, and then show that there is a limit for this functor if and only if, well, let's introduce another functor, Q. This will be from the category of cones, just the projection to the C. So you take a cone here and send this cone to the vertex. Let's call this functor Q. So then there is a limit for this functor if and only if there is a co-limit for the projection functor. So if you think that the problems that we discussed too easy, you can try to solve that one.
both being terminal objects.
Yeah.
Что эквалайзер частный случай был бы просто, нет?
Well, the statement is saying that you can reduce one to another. I'm not sure what you mean in particular case. Well, pullbacks are particular case of equalizers, and equalizers are particular case of pullbacks. That's the statement. Remember how I proved this theorem at the end of the last lecture? I was starting with the general limit, and I was showing that the category of cones for these general limits is the same as the category over some particular equalizer. So you can do this. Well, of course, you can immediately use this to do proof in one direction, right? Because pullback is a limit, and any limit can be reduced to equalizers and products. But you cannot. But you can ignore this proof of the theorem and do this directly.
Can you do it by just showing some arrows on?
I would say that the best way to show this is that you want, for example, you want to show. Well, suppose you have equalizers, right? You want to show that there are pullbacks. Well, can you express limits over the corresponding diagrams for pullback diagrams as a cones, which are cones over some equalizers? Again, showing that the two categories for cones are actually the same. I think that's the general idea that works in all such theorems.
Yeah, but this kind of sounds too complicated. I was like generally trying to just like draw one commutative diagram, then like say that well there is an equalizer, so like let's say I have like two arrows between like two objects, so I have an equalizer, and then trying to prove that this equalizer will like be something like pullback.
Yeah, but when you were trying to do this, you realize by the computations that the two categories of cones are the same.
Maybe yes, but that's kind of.
Okay.
Suppose that we have pullbacks, then I show that we have equalizers.
Mm-hmm.
In other direction. Suppose that we have equalizers, then we have pullbacks. Switch diagram, and then also I have products. And I can consider two maps. One map is X, and another map is the to Z. Then let's consider equalizer T.
Mm-hmm. Yeah, that what I was saying, that you have this diagram, the pullback diagram, you can consider cones over this diagram. And from this diagram, you constructed this new diagram. And you consider cones over these diagrams, over this diagram, right? And the cones are actually the same. That's the point. And
I still honestly don't I understand this proof, but I don't understand what we are saying about cone. Like, why are they the same, and like what kind of statement is that?
no, well, you just start with the cone here, right? It will be well, a cone for the pullback.
Yeah, what do you mean? Like the diagram, like you take another point and like write rather
Yeah, when we discuss limits, there are kind of hierarchy of three data. You have a fixed diagram, you have a cone over this diagram. So in this case, it will be just an object and two projections. And then there is another cone, and you need to check the universality condition. So if you have a cone over this diagram, you can show that it's exactly the same thing as a cone over this diagram. The conditions will be just exactly the same.
So meaning that if I have T
You don't really need this TZ because you obtain this as a composition, right? Every triangle is commutative,
yes.
so TZ you get automatically. Essentially, you have just two projections.
Now, can I finish this?
Uh-huh.
So T is pullback because we have what this is. And this diagram is commutative because of E or N. And if I have T, I can consider such map in product of X, Y, and there is a unique U such as this diagram is commutative. And so O E by X is dx because I can consider projections from this product to X and Y.
Okay. Do you have any questions about this solution? I think the solution was that suppose we have product and equalizers, we want to understand that we have a pullback of this thing. Then the claim was you start with the product, this product which exists, right? And then from this product you have these two maps, and you can take equalizer of these two maps. So the universality condition for this is the same as universality condition for T. I think that was the proof. I suggested a little bit different proof. Well, if you just start, take category of cones over this given diagram. I claim that this is the same as cones over this thing. If you just apply the definition of a cone to the left-hand side, right-hand side, you get exactly the same data. And if the cones are the same, they have terminal objects at the same time. Okay.
And why is it obvious that these cones coincide?
No, that's not obvious. It's just some computation. And I'm not saying that this is obvious. No.
Well, I think every problem in category theory just boils down to actually unwrapping all the definitions and then seeing that this is obvious.
Yep. You have a proof? Mhm.
because it's in direct product of x and y, such that the same because that is by definition of check and provide
Mhm. And I think that this is a little bit easier to understand than what you suggested in the beginning. No, I'm saying, isn't this the second proof much easier, right? You just see that the cones are the same. Yeah, and if you want to go in the other direction, well, what you need to present you need now present that the cones for the equalizers can be somehow reduced to the cones for pullbacks. Well, I think that this works. Why? No.
It doesn't make much sense. What are the errors?
Well, I'm drawing the arrows. Again, you just check that the cones are the same, hence the result.
I actually think for so if you want to show that if we have pullbacks, we have equalizers, it is even it is even more trivial. So consider the diagram, the equalizer diagram. Yeah, we have two arrows from x to y. As
Mhm.
so if we consider this diagram like this,
Mhm.
then the pullback.
Для эквалайзера нужно, чтобы...
Then the pullback will exactly be an equalizer.
Погоди, для эквалайзера нужно, чтобы там отображение в x лог стороны было одно и то же. По-моему, у тебя pullback этого нет вообще.
Oh yeah, actually I see. Might be the problem.
Yeah, that's why you need the diagram I draw.
Yeah.
Second diagram.
Yeah, I see now.
Well, anyway, so if you have this idea, you understand the previous proof, you can check that small computation also proves this second identity between cones. Okay, maybe let's move to another problem. Let's do example as simple as possible. Take the identity factor and compute if the limit of the identity, if it exists, and also explain when it exists.
It should be the third logic, right?
Why terminal?
Well, because you have to have an arrow from each object of C. And it has to be universal as such.
No, I don't think this is correct.
Мне
Notice, by the way, big change in our seminars. Before, our problems were just applications of a category theory as a language to other areas of mathematics. And now we're doing purely category theory without any applications.
We need to define the conditions when the limit of C exists.
Yeah, but I would try to compute this limit, and from the answer you immediately see when it exists. There's definitely some canonical data associated to any category, right, if it exists.
Like existence of terminal and initial objects.
Yeah, for example.
Because the limit wouldn't exist if there is a one.
I don't understand what you're saying.
Yes.
I think this works, but it's not the most general condition.
Is it problem to find, well, I think I have a sufficient condition, but I'm not sure that that is necessary.
Okay, let's start with the answer. What's the answer?
Well, if C has a zero object, then zero object definitely suffices.
Okay,
But I'm not sure that this is necessary.
it's definitely not necessary. Well, what if you try to solve a more general question and then derive this as an easy application? What if you try to understand the limit or some I, and I0 in I is initial object? Can you compute the limit in this case?
Well, this is definitely the limit show object.
Yeah. What if you just apply this to the first problem? So the limit is initial object in C, which is quite interesting because the limit is a terminal object somewhere, and initial object, well, it's initial object in the category, so initial object is a colimit. So existence of some limit guarantees existence of some colimits. No, this last problem is definitely not hard at all. Yeah, I think you immediately get the cone. You just need to check the universality condition, which is also very easy to check.
So, I would like to prove that, the limit of the functor exists if and only if C has an initial object.
So wait, you're trying to solve the first problem or the second problem?
Well,
Oh,
I accurately show that this is true in this case.
how about this? Because if this is true, then this is immediate.
Well, yeah,
Do you have a proof for this?
but
Well, now I'm interested in the proof of the second statement.
well, okay, I think, well, I'll
Ah.
better try there and come back.
Again, I think that this second question is quite elementary. If you just start with the definitions and write the definition, you'll get immediately a solution.
For some reason, the second problem seems more trivial than the first one, even though the first one is a special case of the second one. So
That's the beauty of a category theory.
So if we want to show the second one, well, what do we have? Let's consider the category of codes over D. So a cone over D. Well, I claim that just the category of cones over D is just isomorphic to the category, well, something like slice category over D of I0.
That's not how this works.
Well,
The category of cones is the comma category for the functor delta
well,
and this given functor z.
well, yeah, but I claim that in this case, this is true.
In this particular case,
Yeah, what I want to say is that cone over D,
yeah, I think that works.
cone over D, is completely determined by the map from X to the image of I0.
Mm-hmm.
Well, because such map has to exist, yeah, because this is a cone. And now any other map, since, well, let's take some other object, I1, and the map F1 from X to I1 has to be a composition of
Mm-hmm.
So if we know F0, we know every other font. And now the problem becomes trivial because we definitely have a terminal object here. It is just 0.
Mm-hmm.
Yeah, but for some reason, when I try to show that an initial object is the limit of this functor, well, I stuck on the problem. So suppose z is an initial.
Mm-hmm.
Z is an initial object. So yeah, it has a unique arrow to every other object. But suppose z prime is also also corresponds to a cone over the category.
Mm-hmm.
How do you show that there is a unique arrow?
Well, maybe you can answer to this question again in this generality. I would say that this is much simpler for me. Well, we have this is an initial object, so there is a unique map here, right? To any other object.
Yep.
This is in the indexing category. I just apply D to this thing and call this PI. Oh, that's a cone.
What is it called?
This thing is a cone over D. Oh, I have an object.
Yes.
I have projections to everything.
This is the
So so to check that this is a cone, I also need to check that there is a commutative triangle for any map U. Well, this is du. But definitely this works since this is a unique map from the initial object. So this triangle is commutative, so this thing is a cone. So I need to show this is a limiting cone.
Yep.
So let's erase this part of the diagram. And now showing that this is a limiting cone is more or less the question you asked. Right? Because suppose I have some z and I have zi, some other projections. I want to show that there is a unique map here, right?
Well, but this is the map that corresponds to the data of the cone.
Yeah, so this is z, I not.
Yeah.
Well, there is still a question why this map is unique. Well,
Well, because it has to commute with identity map on D of I naught.
yes.
Yeah, so this also works here. And
Yep.
it's fine.
Can I ask, so if you have an initial object, functor of initial object, the image might not be an initial object.
Of course. But this is not even the problem here. Well, I would say not even related to what we want to do here, because we start with an initial object and the limit, remember that this is a terminal object in the category of cones. So this is why this is an interesting question, because we relate again limits and colimits. Initial object is an example of a colimit. It's a colimit of an empty diagram. And we can present this colimit as the limit of something. Of course, notice that the problem here that the C is not necessarily small, so this is not a small limit.
And how did we get ZI0
Uh-huh.
from Z to D?
Well, we have all these maps, right? In particular, we have map of
because DI0 is also in the.
Yep.
This, okay. And why is it? We also need to show it's unique, right?
yeah, because whenever you have a map like this here, and this is a commutative triangle, you just choose a situation where I is again I0, then this is a unique map which is identity.
Okay.
So then you get the map, identity, and the same map. So whenever if you put any other map here, it has to be the I0.
Yeah, I think that's how uniqueness is proved.
Yeah, of course, you can do this in the dual situation. If you try to compute co-limit over category I that has a terminal object, this is just the value of t on the terminal object.
I think we can actually loosen the condition for a category C. I think if there exists not necessarily initial object, but just an object having a morphism to any other object, not necessarily unique, but just any morphism to every other object.
And can you show the uniqueness of this map in this situation?
Yeah, because it also has to compute with identity. It doesn't use.
How do you know that this map will be identity? If you take I to be equal I0. Because if this is an initial object, I know that there is a unique map, and this unique map has to be the identity on the I0.
Oh, so you mean, the code is not, the code corresponding to this object is not well defined, right?
I think, yeah, that's also a problem. You can take this data, right? Then there's a question why this data is a cone. So why there is a commutative triangle that I draw in the beginning. Okay. I think I wanted to solve another problem. Maybe this is from the previous chapter, but I still think this interesting question. And I'm going to use this category on the next lecture. So maybe it's better if you try to do some computations with this category. So remember that I said that any categorical question is a question of existence of a universal object, initial or terminal object. How about representable functors? So suppose I have a functor representable if and only if the category of elements of F, I'm going to define this in a second, has, I think this is initial object. Let me check this. I can be wrong about this. Is this initial or terminal? Yeah, this is initial object. So if the category of elements of F has an initial object, now let's define this category. So objects in the category of elements of F, these are pairs, C and X, where C is an object in the category C, and X is just a point in the set which I obtained by computing F on the C. And if I want to say what's a map, say phi, between Cx and C prime x prime, well, this is a map in the category C, such that I have a property that if I apply functor f to this map phi and compute this on the point x, I'll get x prime. By the way, this is also a comma category. So functor is representable if and only if some category has an initial object. Well, in this case, we assume this is a covariant functor. It means that there is a natural isomorphism of this functor with the functor hx. So in other words, if you want to compute this on some object, say C, then this is formed in the category C from the x to the C. So x is a representing object. Maybe x is taken for a point, so maybe let's call this t. Just maybe one more time I want to emphasize the logic. At the end of the first chapter, we reduced the question of existence of adjoint functors as existence to initial objects in some common categories. Limits and colimits are by definition some terminal and initial objects in some categories. And now we're reducing the question of is the functor representable, again to the same question, is the initial object in some auxiliary category.
Is there an analogous statement when we reach category not over sets but over
Yeah. I think almost every statement of this kind has a version of it. Well, that depends on your category. For example, if you take a category of vector spaces, I think the element is clear.
Oh, yes.
And when it is not clear, for what categories?
Oh, you can reach over some.
You mean in reach over some category which is not concrete category, right? Yeah, then. Yeah, I think you still can do this in some sense. Well, because here, if we interpret this as a comma category, then this is singleton and F, right? This is this comma category. So now the corresponding diagram would be sets. Now here you have 1, you choose element in the sets. Here you have F, C. So probably you start with some category, you have some category of which you consider enrichments, and then you need to fix somehow a functor.
But this doesn't work for vector spaces because we cannot distinguish elements of vector spaces by there's no well we cannot identify elements of a vector space with maps from some vector space to a vector space because the one-point vector space is actually initial. It is the zero object.
Yeah. I don't see how you can do this without this requirement. So probably you need to put something quick. You can identify your elements as, or maybe you can try to generalize this. Well, just replace this functor 1 and from the 1 to the sets with stuff by other functor which is maybe in some sense look like elements. I don't know. Okay. Mm-hmm.
Because
Mhm.
And the because this is an initial object, this map is bijection of two sets. And now I would like to show that it is matched up. I have not hidden from two lines. And I would like to show that this square is commutative. So what is if I have G there, then attach from X from R is F attached from G from A, and because F is a function, this is F from superposition of F and G. But this F from Z maps to G from Z maps to FGZ. So it is Fy from FG.
Mhm.
So I have an isomorphism between two functors.
Yep. And my plan for the next lecture is to show that if I take any functor from a category to sets, then this is actually a colimit of representable functors. And the colimit is taken exactly over this category of elements. So then this problem becomes completely trivial, because I can compute colimit by computing this on the initial object. So think about this as a little preparation for the next theorem. Okay, I think I have the last problem for today. So the last problem, take X to be a G set, and well, we can interpret this as a functor from G to the sets. So what's the limit from G? What's the limit of X? If this is too easy, there is also a question, what's the colimit? It has only one object. How is that initial? Well, it is initial only if the group is trivial. Well, this is a category with only one object, right? And elements of G are just arrows. Now, what's the functor here? It takes this object and sends this to a set here. And this is a G set because you also maps to the maps. Map here is just an element in G, so it's supposed to act on the image. So this is how you can interpret any G set as a functor. Hmm?
I think I've solved both problems, both the limit and correct.
Okay, tell us.
Well, am I right? So I think the limit are the invariants and the colimit are the co-invariants.
What are co-invariants?
Well, it's a quotient by, well, it's just the space of coordinates.
Yes.
Well, let's again consider a category of commons of this functor. So, what is it called? What is this functor? First of all, we have well our G set. Yeah, and we have lots and lots of maps here. Each of them corresponds to multiplication by an element of G, and cone over such diagram is a map. Well, is a map sets phi from S to RG set such that, well, for every G in G, we have the following condition. Well, if we first take phi, then apply G to it, we also have to, we must be still left with phi.
Mm-hmm.
Well, that is by definition of what it means to be a co. And so now, obviously, well, any such phi actually maps to, well, a subset of invariants under the action of G. So, well, just quotient of RG set by the action of G.
Mm-hmm.
Well, it's a standard fact, that for sets, when we have a map that respects the equivalence relation, it can be factored through the quotient.
Mm-hmm.
Yeah, so, and we see that any such psi can be factored like this. Moreover, the standard fact from set theory also includes that this arrow must be unique.
Yep.
Yeah, because because if we I don't know, name this arrow something psi of the class of x is just psi of x.
Mm-hmm.
We have no other choice. So there is a unique such map for every psi. Thus, this is the continuity.
Okay. So I think we're out of time, so let's finish and continue next week.
Thank you very much.
Sure, you're welcome.